In this video I am going to discuss about a very important part of linear algebra. Now today's topic is what? Test for diagonalization. As you can see, I have mentioned the title. Now here I am not going to discuss about any theory because it is very important for your examination. That's why I am going to discuss about the basic technique of solving the problem of diagonalization in brief. So here you can see initially I have given two conditions by means of which you can test the diagonalizability of any given matrix or sometimes of any given linear mapping. Usually two types of question may come in your examination. First of all, you may be given a certain matrix from where you have to test the diagonalizability. Now in the second part it may happen a certain mapping will be given to you. Obviously you can say T maps from V to W where V and W will be assigned by means of certain vector spaces. Then you have to find out the associated matrix of that linear transformation, whether it is diagonalizable or not. Now the question arises here, whenever we want to test the diagonalizability, I hope all of us we know that whenever we have distinct eigenvalues corresponding to the characteristic polynomial, or better to say after the formation of characteristic polynomial, what you have to do, you have to find out what? Characteristic equation. Now simply you have to solve that characteristic equation to get the eigenvalues. Now there is a standard result, I hope we all know this, that whenever each of these characteristic values or eigenvalues are distinct, then definitely the structure is diagonalizable. But it doesn't imply that whenever you are getting identical eigenvalues, for instance 1 1 2, I am considering a 3 by 3 matrix and then I am considering its characteristic equation and the outcome is supposed to be 1 1 2 as its eigenvalues, then it is not necessary, you cannot say that the given structure is not diagonalizable. It is mandatory that if the eigenvalues are distinct, then it is definitely diagonalizable. But even if the eigenvalues are identical in some cases, for example as I have mentioned 1 1 2, then it may be diagonalizable or may not be. So we need a concrete result by means of which we can test whether the given structure is diagonalizable or not. That's why we have this alternative criteria, and this particular technique is very useful for other competitive exams also, not only for honors examination but also for different competitive exam like NET, SET, etc. So here you can see I have written that the first condition is what? The characteristic polynomial of the linear mapping T should be splitted. That means you can decompose it into different components or parts. That means it can be factorized. And the second condition is what? After solving the characteristic equation, definitely you will get different eigenvalues. Say those eigenvalues are nothing but lambda. Now these eigenvalues lambda will correspond to T, and the corresponding multiplicity of lambda will be equal to what? N minus rank of T minus lambda I. Now what is the meaning of N? This N is nothing but dimension of V minus rank of T minus lambda I. Now this result is very important. Later you will see how can we implement this one. So in order to realize these two conditions, I have given one such example. Suppose imagine this particular matrix is given to you and you have to test whether the given structure is diagonalizable or not. So the given matrix, as you can see, it is 3 1 0 in the first row, 0 3 0 in the second row and 0 0 4 in the third row, and it has been taken from 3 by 3 space of all 3 by 3 matrices having real entries. That's why belonging to M of 3 by 3 within bracket I have written R. Now obviously you can imagine these elements are chosen from R, and obviously this is a part of the 3 by 3 matrices. So technically dimension of V can be considered as 3 in this problem. Now what you have to do, you have to find out the characteristic polynomial of this matrix. Now we all know how to find out characteristic polynomial. Simply consider the diagonal elements, put some constant, you can choose lambda. Here I have written T. So 3 minus T, 3 minus T, 4 minus T. As you can see, diagonal elements are modified, other elements are same. So simply expanding you will get T minus 3 whole square will appear, as well as T minus 4 will be there. So technically you can factorize this expression. So the first condition where I have written that the characteristic polynomial of T should be splitted, that condition will be satisfied. So intentionally I have written this is the first condition, and because of this I have written refer 1. That means the first condition. Now the two eigenvalues corresponding to these two structures are supposed to be lambda 1 is equals to 4, lambda 2 is equals to 3. Here I have given the equation in terms of T. You can also write T1 is equals to 4, T2 equals to 3, but in order to understand the second condition, because I have written the second condition in terms of lambda, that's why intentionally I have written lambda 1 is equals to 4 and lambda 2 is equals to 3. So first of all you have to identify what will be the algebraic multiplicity of these two eigenvalues. That means you can see 3 occurs twice, that means the algebraic multiplicity for 3 will be 2 and algebraic multiplicity for 4 will be 1. Now just find out rank of t minus lambda I. Now here there is no t, instead of t you are given a certain matrix A, so that's why I have written A. Then you can see lambda I is there. What is the first value of lambda? As per our assumption, that is lambda 1. So A minus lambda 1 I, this will be the first part. A minus lambda 2 I, this will be the second part. So A minus lambda 1 I, already you know what is the value of lambda. So just put lambda 1, that is 4, in this expression in the diagonal parts. So 3 minus 4, that will be minus 1. 1 0, keep these two things intact. Again in the second row 3 minus 4, that will be minus 1. But in the last part you will get what? Because lambda 1 is equal to 4, so 0 0, 4 minus 4, that is 0. So here you can see, as you have obtained two non-zero rows, even after modification you cannot get lesser number of rows. So that's why you can say, as you have obtained two non-zero rows in this expression for A minus lambda 1 I, that means rank of this expression is bound to be 2. By similar technique you have to find out rank of A minus lambda 2 I. Here you can also see that I have used lambda 2 is equals to 3 in this expression. So put t is equals to 3. So 3 minus 3 0, 0 1 0 will be the first row, 0 0 0 will be the second row, and 0 0 1 will be the third row. So here also you can see two possible non-zero rows are attainable, and that's why rank of A minus lambda 2 I should be equals to 2. So the criteria is what? N minus rank of t minus lambda I. So what is n? Remember I told you this is equivalent to dimension of v. What is v? In case of any linear mapping, t maps from v to w. V is nothing but the space from where the elements should be taken. So here you have chosen the space of 3 by 3 matrices, so dimension of v will be 3. So that's why you can see I have written 3 in place of n. So minus rank of A minus lambda 1 I, that means A minus lambda 1 I's rank is what? 2. So 3 minus 2 is equal to 1. Now in the second case, again n is equal to 3, minus rank of A minus lambda 2 I, that is 3 minus 2, that is equal to 1. So technically you can see multiplicity of lambda 1, this is equal to what? Obviously multiplicity of lambda 1, that is 4, that is equal to 1. What? That means we are considering the algebraic multiplicity of these two eigenvalues. So you can see in the first case multiplicity of lambda 1, which is supposed to be 4, that is also equal to 1, and this particular condition is also equal to 1. So for the first eigenvalue the condition is trivially satisfied, but for the second eigenvalue the condition is not satisfied at all, because 3 minus rank of A minus lambda 2 I, that is equal to 3 minus 2, that is equal to 1, should not be equal to algebraic multiplicity of lambda 2, because already you have seen algebraic multiplicity of lambda 2 is what? 2, and hence you can say A is not diagonalizable at all, because it should be true for all possible eigenvalues. Then only you can say the given matrix is diagonalizable. So this is a certain technique by means of which you can identify whether the given matrix is diagonalizable or not. Now there is another type of problem where initially the matrix is not given to you, rather you have to determine the matrix initially. So here you can see in the second question I have written, let t be a linear operator defined on P2R given by t of fx equal to like this. You can observe the structure f of 1 plus f dash 0 x plus within bracket f dash 0 plus f double dash 0 into x square. Now what you have to find out? You have to find out initially the matrix B, which is obtained by means of this linear transformation T, or you can say this is the matrix representation of this linear transformation T or linear mapping T with respect to the ordered basis alpha. And what is alpha? For your reference, it is also mentioned in the question that alpha is nothing but the standard ordered basis for P2R. Now simply remember what is P2R. P2R represents the space of all polynomials having degree 2. That means you can say the general member of P2R can be taken as ax square plus bx plus c, and thus we can say the elements of alpha can be taken as 1x and x square. So here you can see there is a basic difference between these two problems. In the previous problem the matrix is already given, whereas in the second problem the matrix is not given to you, so you have to form it. So that's why first, using this definition, you have to find out t of 1, t of x and t of x square. I am not going to provide the details of the formation because already in the previous video what I have uploaded yesterday, you will see that the result will be already mentioned there. So technically you can see t of 1, whatever we have obtained here, that can be expressed as a linear combination of 1 plus 0 into x plus 0 into x square. T of x, that is written as 1 plus 1 into x into 1 into x square. By simple calculation you can obtain all these things. Then finally t of x square is like this. So just consider the coefficients. In the first structure you will find the coefficient is what? You will find that the coefficient is 1 0 0, and in the second case the coefficient is 1 1 1. That's why you can see in the second column I have written 1 1 1. In the third case the coefficient is obviously 1 2 2. Then sorry, 1 not 1 2 2, 1 0 2. That's why in the third column you will see it is, I have written it is nothing but 1 0 2. So here you can see that b is equal to like this 1 0 0, then in the second column 1 1 1, then in the third column 1 0 2. So first of all we have to find out the characteristic polynomial of b. That means simply consider the diagonal, that will be 1 minus t, 1 minus t, 2 minus t, and then accordingly you will get the expanded version, that is 1 minus t whole square into 2 minus t. Just take minus common, then you will get minus of t minus 2, t minus 1 whole square, and hence you can say the original characteristic polynomial has been splitted in the form of like this. That means the first condition of diagonalizability is satisfied in this case. Now moving on to the next condition, what you have to check, for lambda is equals to 2 and lambda is equals to 1, I have renamed them as lambda 1 equals to 2 and lambda 2 is equals to 1, that are two eigenvalues. We have to check their multiplicities. Again I will say this multiplicity is not geometric, this is simply algebraic multiplicity. So for lambda 1 is equal to 2, you will see it will occur only once, so it has algebraic multiplicity 1. For lambda 2 is equal to 1, it has algebraic multiplicity 2, because you can see t minus 1 squared, this type of expression is already there. Now simply use lambda 1 is equal to 2 in the expression of a minus lambda 1I. Now why I have written this one, remember in the last problem also I told you, you have to find these two expressions, then the associated rank, then you have to verify this condition, n minus rank of t minus lambda I. So a minus lambda 1I, how to determine this value? Already you have obtained t is equal to 2, so put t is equals to 2 here, accordingly you will get this matrix. Now by simple elementary row operation, here I have operated one such operation, that is r2 dash is equals to r2 plus r3, so that you can see second row is 0, and technically, or you have obtained only two non-zero rows. Even you can perform one more additional operation, you can subtract the third row from the first one, but still you will get two non-zero rows. So rank of this expression will be 2. Then n minus rank of this expression, n is what? Because you are considering p2r, so how many elements are there in the basis set? Obviously 3 basis elements are there, so that's why you can say dimension of v will be considered as what? Dimension of p2r, which will contain 3 distinct elements. So 3 minus rank of this expression, that is equal to what? 3 minus 2, that is 1, and hence you can say it is equivalent to the multiplicity of the first eigenvalue, that is for lambda 1 is equal to 2. So in a similar manner you can also satisfy the condition, this condition for the second eigenvalue. I have also explained this one. Here you can see a minus lambda 2i is obtained, rank of a minus lambda 2i, that is also 1, then n minus rank of a minus lambda 2i, that is 3 minus 1, that will be 2, and you can see for lambda 2 is equal to 1, you have also obtained multiplicity of lambda 2, and this thing is identical. And so you can say for both the eigenvalues, both these conditions what we have mentioned earlier are satisfied, and hence definitely the given structure is diagonalizable. That means this particular matrix is diagonalizable. Now, so we can say If the matrix is diagonalizable, that means T is also diagonalizable. Now sometimes we need to find out the associated eigenvector. So for that purpose I have given this illustration how to find out the eigenvector. So I have written to, now let us consider an ordered basis gamma of R3 corresponding to the eigenvectors of B. Already you know two eigenvalues are attainable. One is lambda 1 is equal to 2, another one is what, lambda 2 is equal to 1. Now the necessary eigenvectors can be written in the form of like this. Obviously they are column vectors, and the vector space that contains these eigenvectors can be termed as eigenspace. So you can see I have written for lambda 1 is equal to 2, the eigenspace is what, E lambda 1, and the second eigenspace is what, E lambda 2. Now what is the meaning of E lambda 1? You have to choose the column vector from R3. Now obviously lambda 1 is equals to 2. How to attain this one? Simply put T is equals to 2 in the first expression. So minus 1 1 1, 0 minus 1 0, 0 1, and obviously lambda is equals to 2 or T is equals to 2 means this part will be 0, and accordingly you will find this type of expression. Now obviously the column vector x1 x2 x3 will be there, and on the right hand side you will see I have given the components of null vector. Now just simplify this expression, then you will get a system of equation. Now x2 is 0, and for the first component equation you have obtained minus x1 plus x2 plus x3, that is also equal to 0. Because you have obtained x2 equal to 0, automatically x1 will be equal to x3, that is equal to k. We have taken this one. Obviously k is non-zero, so for sake of definiteness we can consider k is equals to 1. Accordingly x1 x3 becomes 1, but x2 is already 0, so you can say gamma 1 is the first basis vector, which is supposed to be the column vector of the form 1 0 1. In a similar manner, or similar by means of similar argument, you can also find out the second eigenspace, that is supposed to be E lambda 2. Now you can see in case of E lambda 2 we have obtained x1 plus x2 plus x3 is equal to 0. Now here you have three different variables, but only one equation is attainable, so you can consider two variables are arbitrary. So I have written that thing. Now it's up to you which variable you want to choose as arbitrary variable. So initially I have taken x1 is equal to 1. For the second part I have taken x1 is equal to 0. Whenever x1 equals to 1, x2 x3 are simultaneously 0, so 1 0 0 is a possible component. Again x1 is equal to 0, then x2 and x3, they are opposite with respect to each other. So if I take x3 is equal to 1, then x2 will be minus 1. So you have obtained gamma 2, which is a cluster or combination, or better to say a set of two column vectors 1 0 0 and 0 minus 1 1. This is a new modified basis. Now here one question may arise, how can I say they are linearly independent? Obviously you can see one column vector cannot be expressed as a scalar multiple of the other, that's why definitely they are linearly independent. Now the final resulting structure of gamma that can be obtained by taking the union of gamma 1 and gamma 2 will be like this. And so you can say that gamma is nothing but an ordered basis of R3 consisting of all possible eigenvectors of B. Now you can say up to this you may have to calculate in your examination. Also sometimes you need to find out the coordinate vectors relative to the original basis vector alpha. So in the next part I have written, now the vectors in gamma are the coordinate vectors relative to alpha corresponding to the vectors of the set beta. Now how you can obtain this one? Simply remember what was your first part, 1 0 0. Imagine this is the coefficient of 1, this is the coefficient of x, this is the coefficient of x square. That's why 1 0 0 will ultimately give you 1 into 1 plus 0 into x plus 0 into x square. So we have obtained 1. In the second case, 0 into 1 minus 1 into x, 1 into x square. So minus x plus x square. In the third part, 1 into 1, 0 into x, 1 into x square. So we have obtained this one. So this particular set will behave like an ordered basis corresponding to P2R with respect to the eigenvectors of T. And so if you want to find out T of beta, then you can take the help of this particular elements, and also you can use this definition. So using this definition and obviously using the final structure, whatever you have obtained here in terms of beta, you will be able to find out this matrix. But it may not be necessary, But one thing you must remember, whenever you have to test for diagonalizability, first you have to check the characteristic equation whether you can split it in a proper manner or not, and number two, as I have mentioned several times in this video, this part must be satisfied, and if this condition is not verified for each and every eigenvalue, then you cannot say the given structure is diagonalizable. So this part is very important. It may come in your examination, so I suggest you please go through this video for your own convenience. And obviously there are several other techniques of diagonalization, different theories are there, and I am considering only these two problems because they have special technique and they follows a special approach. That's why hope it will be beneficial for all of you, and thank you and best of luck.